Okay, the German approach to mechanics begins after our wonderful break, which is the Riemann and Christoffel and all of that geometry that's so much a part of our way of doing relativity. But also, if you're going to work with a manifold like the trebuchet torus that's on the screen down here at the end of the room, you're going to be working with coordinates that are rarely orthogonal, mostly non-orthogonal, with little cells that have twisted shapes to them that involve a curvature of the manifold. So what we're going to discuss today are the properties of the mathematics that the coordinate, the generalized curvilinear coordinates really need to be used even when you're not talking about relativity. And these weird things called Christoffel coefficients, I would shorten that name if I could. They're simply Coriolis coefficients, and that will prove as we finish our discussion of the nitty-gritty of the rules that you have to follow. And these rules are tensor rules, but they're really, the rules are how do you transform one manifold to another? What are the rules for that? And once you've established those rules, which we've already seen, it's just products of Jacobians, but once you've done that, then what are the things that you could, what are the pitfalls? And one of the pitfalls is to think of something that has three indices as the third rank tensor. Christoffel coefficients have three indices, but as we're going to see, they are not tensors. So we have to discuss what's a tensor and what's not before we go too far with this development. And then the real thing that I want to show today are the Christoffel equations. Well, they should call it Christoffel equations because they have those coefficients. But they're generally named Riemann equations. Riemann equations of motion. So this is the German way to say F equal ma. And that's what we'll learn today. And of course there's covariant and contravariant ways of doing that, as we'll see. Then the rest of the lecture today will be more fun in the sense that we'll show some movies, including ones that come from outside. I'd like to show a movie of the vortex, but in a swimming pool. This is something that I tripped over on the web just by Googling vortex, and you'll see you can look at some more of the things that follow this up. It's a site called, what is it called? Girl Physics?
Physics Girl.
Physics Girl. Okay.
Subject.
So you're going to meet the physics girl who, to her credit, has taken a lot of things that physics courses use, including some things they don't use, and made them very attractive. That includes the problem that we did on the vortex. Okay, so let's go ahead and look at what the problem is here, and that is that if you're going to take a generalized coordinate derivative, that is, take a derivative with respect to a contravariant quantity, and that's all you have in the formalism as presented by all of the books that use this generalized tensor analysis, you have two things that vary. If it were just the coordinates changing, then you'd go like Jackson, and that would be the end of the story. There's the partial derivative of the component with respect to Q, and then there's some unit vectors that, if it's the Cartesian unit vectors, are there. But for all of the other ones, all the ones that have any curvature, you got to worry about the second term here. And that's the partial derivative of the supporting manifold vectors, either the tangent space or the, we'll get to that, the contravariant normal space. So Christoffel coefficients are involved in expressing this in terms of the vectors that span the GCC. So what we're going to do is express this particular derivative here, which is with respect to a contravariant quantity. One of the ways is to use a contravariant linear combination. If you do that, you write this thing, which is called the Christoffel coefficient of the first kind. And then the second kind is one that's used to expand it if you want to expand it in terms of covariant vectors like that. So that's what we've got to learn right off the bat here, is these two kinds of coefficients. Now, just out of curiosity, how many in the class have worked with something like this? Has anybody here done anything with this? Okay, so this is new. I'll take it slow. It's a thing that is very much a part of our mathematics. And as I say, there are two kinds here. One of them is the expansion coefficients of this derivative in terms of covariant vectors, and the other one, the first one, is an expansion, which you might call the covariant Christoffel, but they're not tensors, so you can't really do that. But in any case, this guy here, first kind, is expansion coefficient in terms of contravariant vectors. Now there's just the other way around. So, one of the things that you should note, though, is that some of the tensor properties are valid for the Christoffel coefficients. And that's where you use either a low index, which is a covariant index, or a high index, and the relationship between these two is just simply the relationship between the contravariant and the covariant vector. In other words, the metric tensor that's contravariant takes a covariant thing after you've summed over the dummy index L in this case, and gives you a contravariant vector. So these are the linear combinations between what we've been jokingly called bras and kets. There is a way to make linear relations between bras and kets. It's not very popular, and we'll talk about that later when we discuss eigen solutions in general. But for now, we do have that. And we also have, going the other way, I can take a contravariant guy and tame him down to the covariant by using the standard covariant metric tensor. Well, that works for one index on the Christoffel symbol. It does not work for the other two. We don't even discuss a contravariant double index part to this. That would be the third and fourth kinds of the thing. I've never seen anybody carry this out to any degree of things. And the other thing that should be pointed out here is that just like the metric tensor is symmetric in its two indices, so you can write that either way and get the same thing. The Christoffel coefficient obeys that too. And it just has to do with this little guy right here, the partial derivative with respect to the contravariant component of, in this case, a covariant vector, or later on we'll discuss the contravariant vector derivative. But the basic idea of that is that if you write the partial derivative with respect to qi of the E vector, and then remember that the covariant vector in any case is the partial derivative of r with respect to whatever index you apply to the coordinate in question. And then saying this manifold is differentiable, continuous and differentiable, remember we can flip the order. And once you flip the order, you've gotten the flip of I and n from n and I. So that means that I can write this thing ni or in, still the same number, still exactly the same thing. So I've written that thing this way. to respect that. And it's true over here as well. Okay, so those are two things that make the Christoffel symbols a little nicer. As you've seen in the homework problem I've given you, the number one problem is to calculate a few of these things. And I've torn my hair while working relativistic problems using these things, in which time I was told that they're not called Christoffel coefficients, they're called Christoffel coefficients by people that work with them. So, okay, with that out of the way, the idea here today is to find easy ways to deal with these things rather than difficult ones. And one of the things that you might notice is, well, if I'm going to be working here with partial derivatives of covariant E vectors, I'd better also pay attention to the normal space. This is the tangent space. I better pay attention to the normal space. What am I going to do there? Do I have a third and fourth kinds of Christoffel coefficients in order to take the derivative of a normal vector? That's a contravariant vector, you see. And then if that were the case, I would write this thing in that way. I would just say, here you see I have an E contravariant. I dot both sides of these of the equations with an E covariant. Then I just get the coefficient free and clear. And there's no summing going on in either this definition right here. But as we find out, and this is what makes it much easier, is that the answer to this question, do we need a third kind? The answer is no. The lambda coefficient is just a gamma coefficient with a minus sign. And the way you prove that is right here. You realize that the dot product of a contra and a co, that's the whole point of having contra and co, is to make an orthonormal, mutually orthonormal pair. So this is a delta function, either 1 or 0, depending on whether these two are equal, and it's 1 or 0 otherwise, right? So we're all familiar with that. But the basic idea is that the partial derivative of a 1 or a 0 with respect to any of our coordinates is identically 0, right? So this new guy in town here is just minus this old guy. So this new thing that we'll use if we want to do an expression in terms of contravariance, which we do very often. We'll be using more often than not the minus sign definition. And that comes up fairly quickly here in this development. And the idea being that when we write this partial derivative u out as a combination of just a covariant a unitary vector, well, these are the two terms, okay? There's the partial derivative of the coefficient, and then there's this combination. In this case, it's this guy right here with the component un being summed over the lower index. That always has to happen when you're doing this sum, just like this contravariant has to match this covariant in an expression that doesn't have any mention of those two numbers that are being summed as a dummy index pair. And so that is one way to express a derivative of a vector with respect to a generalized curvilinear coordinate, of which, as I remind you, we have only the contravariant kind. And I won't bore you with something I did a long time ago where I just made a new coordinate system that was covariant. And it's very neat because they were mutually orthonormal, but big deal. Anyway, because of this, I will be writing, when I expand it, as a covariant quantity with a contravariant vector, covariant component here, sum over m, and then there's the m. And that, you see, has the sum here in the downstairs of the Christoffel coefficient, whereas here it's in the upstairs part of it. Okay, so that minus sign is what you'll see more often than this one. in the literature, most of the literature. Okay, now at this point, I want to point out that this semicolon is, as far as I can see, used everywhere that this kind of formalism exists. And I'm putting a semicolon here when I talk about the covariant derivative with respect to qi. I'm saying um, instead of comma I, which you would do if it was just that thing right there. If this was Jackson's electromagnetism, which is all orthonormal stuff, that would be the definition, but you just have a comma here. You wouldn't have the semicolon, which is allowing you to take account of all the things that will happen in a curve space, and in particular in general relativity, where everything is curved. And same thing over here, there's a semicolon right there. So the Christoffel coefficient comes with this semicolon that then appears in an expression for a derivative that is a tensor. These are both tensors. This is a mixed contra and covariant tensor. This is just a plain old covariant second rank coefficient tensor. And we'll get used to some of those as we look at the equations in motion. So this funny semicolon notation it takes getting used to. Now I'm going to write both of these derivatives together here and bring these two screens in sync. And so that's where we are right now. We have these definitions that allow us to do this operation, that is, take a partial derivative of a vector with respect to a contravariant GCC coordinate, queer coordinate. So this is all queer stuff here. Okay? All right, so far so good. It's a lot of definitions all piled together. Now, mathematicians can't stop being cute when they develop things like this. This is people who came after Riemann, but I think Riemann did this. He thought that we needed to have some sort of first-order derivative for independent, in this case time, we're talking about mechanics here, so we're talking about the really total time derivative, counting all of the crazy stuff a curved coordinate can give you. So we go ahead and we write the thing in terms of the q dot here. In other words, we write this thing with the Christoffel coefficient in there, the q dot here just being the result of asking what happens when I take the extra t here. Anyway, this is the definition of a real time derivative in a curved space that just involves the time derivative of all of the coordinates. And it's this covariant derivative of the component that includes the Christoffel coefficients there. And it works for either the covariant components, which had a contravariant vector somewhere if I've written out the vectors, or this one right here, which is a contravariant, some kind of velocity or force. Okay, so cute Newton 2, this is cute Newton 2, is just contravariant force is equal to the intrinsic derivative of the momentum, the contravariant momentum, which you will see later turns out to be an acceleration. And this one right here, this covariant thing, that really is the canonical momentum in mechanics. So it's the covariant force that is equal to that. So those are the two Newton 2. This is the way you say Newton 2 without getting into the details that this equation here involves. We'll avoid that for the most part. We'll go directly to this thing, have a cool way to calculate the Christoffel coefficients and then get the results that we need. But in any case, you can write this thing as follows. We replace the total time derivative chain sum, okay, which includes all of the things that change, including time. But we're going to find out that we with this formalism can't do that. Time has to be a coordinate to really make it work. But this idea right here is, you know, just our plain old chain rule. Either with a contravariant thing like velocity, so this would be some kind of acceleration, or a covariant thing like this, some kind of momentum maybe could be the v here, and it would be a linear combination like this with the semicolon. But it's replacing the Cartesian version, you see. The Cartesian version is just partial derivative of a vector component with respect to the coordinates and then q dot. End of story. This one's got all that stuff packed in there with the Christoffel coefficients, as does this one here. So that's what's really going on up here, is we're just rewriting things for curvilinear coordinates that we're used to in Cartesian. And you see the minus sign when you're dealing with the thing that's totally covariant. But it's a plus sign when you're dealing with this guy. Okay, so k up, you get a plus sign, k down, covariant, I get a minus sign. Okay, so that's some more contravariant versus covariant that you have to deal with here. All right, let's drive the old formula for Christoffel coefficients in terms of derivatives of the metric tensor. This is the Christoffel G derivative formula, okay? And it turns out that basically all you do is take the derivative of the dot product of two, covariant, or you can go ahead and do this for contra, but I'm not going to go through that. We don't need to, because we'll be making something that have its indices raised or lowered when we're done with combinations of these Christoffel coefficients. Okay, so right away, first we get the product derivative, which has the two sums there, and then we write those as Christoffel coefficients. So here's a formula that gives you this particular sum here, where you interchange m and n on the two sides of the semicolon and add them up. Okay, so you'd think that Riemann would have been happy in Christoffel too to just stop with that, but they weren't. They realized that there's a symmetry in all of these things, so I can go here and make use of the Christoffel symmetry of the first two indices, okay, and write three expressions here, and I've told you what the difference is, and here I switched the I with n, here I switched the I with m, although I didn't really switch the I with m because it doesn't make any difference which order you have I and m in the first two places. The same is true for this one and this one and this one, okay? But in any case, you arrows trace where we've done those switches here and for this, okay? And then the idea of doing these switches is we get a bunch of things that can cancel each other. If I put a minus sign on this equation right here, then what happens is that guy cancels that guy cancels that guy, and I get these two guys equal, okay, so 2 times this thing equals this combination. That's the formula that you'll see listed in any book on tensor analysis. That's the completely covariant Christoffel formula. Now we know how to raise this index only, so if I put another G contravariant on this, sum over it, and I have to put it on this side, of course, and note the minus sign there. It's a very complicated expression of derivatives, and more so than what I said we could have started with. So this can be made into a contravariant formula as well. Now, what's really terrible about this formula is, you see, it is rank 3. That is, there are 3 different indices here, I, m, and n. So even if we're talking about something that's 2-dimensional, okay, we've got 8 of these guys to work out. If you're talking about something that's 3-dimensional, you've got 27 of these guys to work out, right? And it turns out most of them are 0. So there should be a better way to attack this thing than going through all 27 or through all 8, okay? And your first problem on the Christoffels here as you probably looked at, is to evaluate them for spherical coordinates. We're going to evaluate them for cylindrical, but either one of those is going to take advantage of an alternative to this. So please don't use that. You'll be wasting a lot of time. Okay, so this is where the physicist wins over the mathematician, because he knows Lagrange's equations can give this directly. That's coming a little bit later here. Okay, so there's the formula. And then I've got to do some whereas and what fors about these things. These guys are not third-rank tensors. They look like they might be, but they aren't. Whereas all the other things that involve combinations with Christoffel in appropriate orders are. They're the correction coefficients. That's maybe another good name for them. Correction for the curvature, CC. So, question is, what's a tensor and what's not? Well, what is a tensor is the metric. Okay, so for example, if you have to take this to another GCC system that has bars over all of the quantities that are variant, as it were. In this particular case, I'm thinking of the metric that goes with some other coordinate system. Say we've already worked out stuff for the toroid manifold for the trebuchet, but something else comes in that makes us use another coordinate system. This is the issue, is that I want to maintain the tensor properties. And at the very least, I've got to do the transformation from Cartesian to GCC. So I better get that right. That's the original Cajovian and Jacobian. So that's what we're up against here. But in any case, if you have to go from one GC to another, this, what I call chainsaw sum, seesaw sum, okay, big C, saw, sum, okay, is the technique. It's the generalization of the completeness relation you do in quantum mechanics. I already said that once and twice. So we're doing it again here. I just take these two partial derivatives and saw them apart, leaving blanks, diagonal blanks there. And then I stuff whatever coordinate system I want this to be transforming from in there. So I just go ahead and I stick a QM and a QM here, just to match the M bar down here, sort of. And then right here, I've got an N bar here, so I put 2QN. So this would be a transformation back to the original manifold that didn't have the bars designating its framework. So that's a tensor. When you get something that transforms just with products of Jacobians, that is this quantity here, which is this quantity, transforms with just a product of two Jacobians. In this case, one that's got the bars flipped and the one that doesn't. Okay. I'm sorry. In this case, they're both on the bottom here, the bars. I'm thinking of something that's coming up here very quickly. But this would be the G bar, M bar, N bar metric tensor that we started with as a linear combination over, well, a product of two Jacobian components here, but summed over all the M's and all the N's, okay, for a particular M bar and N bar. Now, one of the things as you see is if you're going to play with this stuff, you're probably going to want to play with it on Mathematica. And Mathematica is equipped to handle this stuff. It's really quite amazing. It's the only mathematical language I know of that can do this stuff fairly convenient. And I'm not completely versed in the things that it can do. But in any case, this is a tensor transformation for second rank. You might think there'd be one like that for the third rank tensors. Well, there is, but these guys aren't tensorial. And we have to show that. We have to show what it is that's wrong with these things as far as that goes. But in any case, let's just start off with one which is a mixture of second rank. Okay, I do a seesaw sum to get this bar frame expression here. Okay, this is a second rank some vector u that we're interested in, okay, has a tensor that goes with it that's both contravariant and covariant. Well, that's what this is. This is the example we were looking at before there. It's the partial derivative of u with respect to the contravariant n, so that means I have the n down because this guy's in the basement here. And then I've got a coefficient, this coefficient here is marked for m bar. I'm dotting with a contravariant vector, okay? Now, we'll do all of this again just with this thing as a covariant, but let's do the covariant derivative of a quantity, the um semicolon n. And that seems to have run off the screen there. Let me catch up on the other projector here so you can see it. It looks like it's off the screen too. Anyway, we'll just deal with this. This is what we're actually talking about. The question is, how do you derive this? A seesaw sum derives that. So that's what we'll put in here. Now remember, this is the definition, you see, of the covariant derivative of the components. Okay, we're trying to get away from even looking at the actual unit vectors that the normal and tangential space has, but just working with those numbers, simply in Mathematica, we're going to do all our stuff. The question is, how do you derive a thing like that? Again, same thing that you did up there, essentially. Okay, so here is the definition of the thing. I chainsaw sum the partial derivative. Okay, and then stick in where I want to go. I'm here with the bar guys. I want to get back home where I don't have bars. Okay, and there is going to be one of the Jacobians. But then I already know how to take the E out of bar land into non-bar land, and that's a contravariant E transform. Once again, that's a chainsaw sum as well. Here, I started with that thing, sawed it apart, put in a sum over the unbarred coordinates. Okay, and this one right here is a contravariant. It's got a thing in the numerator, so it matches it straight away. Okay. Remember, this is a gradient of a coordinate, right? That's what the contravariant is, normal to it. Okay, so once I've done that, then I've got the two Jacobians that I need, one with Q bar downstairs and one with Q bar upstairs to match covariant and contravariant respectively. So there's the derivation of that, okay? Now, the other kind that we have, and I'm going to put that on this screen over here, is the seesaw sum for a covariant vector here. Okay, see the covariant vector in this place on that screen. Okay, we do the same thing with its derivative. We do the chainsaw sum. Okay, for it, stick in the QNs that we want to go back to, sum over that, do the covariant E transform at the bottom, and then we get a ordinary kind of second rank tensor. That is ordinary in the sense that it's all covariant. So compare this to what's at the right hand side over there, and you see the partial derivatives have the barred quantities in the lower portion of the partial derivatives. Okay, and the definition of those, and now I'll bring it up on this screen, the definition of those, okay, has the minus sign. That's the covariant case of the covariant derivative. Okay, I think that settles that. So here I'm going to do some hand waving just to say what is a tensor and what is not. This transformation that we just got here is a mixed up and down with the partial variables. Okay, so you see the indices up and down for it. That's quite common. A lot of times that you want to do that, particularly with antisymmetric quantities. And the idea is that the transformation of, this is U-M semicolon N. This is the Jackson way of writing partial derivatives of vector components. U super M, comma N, or very often he doesn't go super. I don't think he does that at all, in fact, so this would just be M down and N down, okay, which is the partial derivative of U, M's component with respect to the nth queer coordinate. This is not so simple in its transformation behavior as this. You say, yeah, well, this isn't very simple and you have to add this thing. But believe me, as far as curvature goes, no other way. Got to add that, as you saw from the very first slide. So what happens? You say, well, maybe we can finesse this. At first it looks possible when I do a partial derivative of that and chainsaw it open and stick in a Qn. Looks like I've done it, you see. But the trouble is I still have a barred quantity in there. I've got to fix that barred quantity with yet another transformation. Then it gets messy, you see. Then I've got to add something that is the derivative of the Jacobian for bars to unbar transformation, you see. And that's where the Christoffel coefficient is going to come in, you see. So you can only pull this kind of simple stuff with Cartesian coordinates for which the Jacobian has no variation. The vectors everywhere all point in the same direction. If that's the case, great, and don't get long or short either. You can pull this off, okay? So this first term is okay. That's a transformation law that we'd like to have, but it ain't going to work unless the second term is 0. Okay, only if the Jacobian is a constant matrix do we get to ignore the Christoffel coefficients, okay? This thing really needs the semicolon in there, and that means you have to either subtract or add a term like that. And that in turn means that this term here cannot be tensorial. So the Christoffel symbols have just the negative of the disease that this partial derivative has, and that's the correction. That's what the correction is giving us. Okay, what is that correction physically? Centrifugal and Coriolis forces. It's due to the curvature. Okay, and that's what we have to prove. We have to show that. Okay? So we're going to use cylindrical polar here to do that. And then I'm asking you in a problem, go ahead and work out spherical coordinates so that you know what their Christoffels are. And not that many of them, as you'll see very quickly. So you don't have to go through all 27 for a three-dimensional system. But this is a point where we now can derive, or I should say develop, Riemann equations of motion. Now, a couple of things I have to say right off the bat here, and that is that the Lagrange equations, the four-wheel drive garbage truck that I'll be putting back here in just a minute, could handle situations where the x, y, and z, that is the coordinates, Cartesian coordinates, could handle a situation where they had explicit time dependence. That is, suppose you wanted to work something out in a rotating coordinate frame. With the garbage truck, go for it. That equation, that force Lagrangian, as I say, works. Just go for it. You can do it. You can't do Riemann with it. It just doesn't work. There's no way you can think of how it would work in the ordinary way. What you have to do is include time as a dimension. So if I come speeding through this room at 3/5 C, I'm going to see you on retarded time. You're going to be on California time. And then just as I pass Millie, I'll look at her clock since she's on my time, Central Time. And then I can get to you, and we're talking Eastern Standard. Okay? So every place in the space is a different time. You can see why you really need to make it a dimension. This is relativistic mathematics. It's capable of handling relativistic situations. Okay? So that's what you do. And then you don't have this partial derivative out of there. You can't have that. You just have this guy and this guy. Okay? You just have this. All right? Now, this already is a transformation from Cartesian to whatever queer coordinates you want to use. And remember we said that we weren't going to get anywhere if the Cartesian matrix, okay, which usually is diagonal, it's just different masses maybe for each of the coordinates, right? But if you're trying to do a problem in band theory where you have dispersion that makes there be off-diagonal terms to the effective mass tensor, then this won't be diagonal. But in order to use such a thing, this guy's got to be a constant. Okay, that's the thing we said when we derived Lagrange's equation. You shouldn't forget that. Okay. So, what we're doing here is producing, and this is a typo here. That's okay, but this should just look like having this guy right here in the mass place. So there should be an X right here. I don't know how I missed that when I was reading this thing carefully this morning. Anyway, that's the thing. So this is going to be our metric. This replaces GMN when mass matrix MIG is involved. Okay, and that's a transformation. Second-rank tensors, covariant second-rank tensors are being used there. Okay, so let's get these things synchronized because the derivation of the Riemann equations is a bit painful in some ways. Not terribly, but great. Basically what we're going to do is use, the Lagrangian to help us. But first, we go through and we look at, and this is what we're really looking at here, is the Lagrange equations written using the q coordinates that we've already derived. And I'm going to go ahead and state what it's these guys. They're fixed. Or if you want to stick with this thing, if you just want to use this, you're done. Okay, the Lagrange force equation, as I say, it works everywhere. But we're trying to carry this thing over, and in that case, I must not have any of that and have anything that's explicit in time. As I say, this is for fixed GCC only. So I go through here, taking the time derivative of this thing, as I'm supposed to do. This is the momentum, so I'm talking about dp dt right there. And then I'm going to be subtracting a partial derivative with respect to q of the kinetic. So it's going to involve the curved GCC dynamic metric, the way we've been doing our Lagrangian stuff here. So writing all that out, I get an equation involving derivatives first. Time derivative of this thing. This thing doesn't. This thing will not be constant because of the q's changing and curving and doing all the stuff they do. And then there'll be this left at the end of that. So see if there's anything missing here. This is just the product derivative here, and then there's this part that corresponds to this thing right there, partial of t with respect to q. Okay. And this guy, derivative of that thing with respect to time. Okay. I do a chain rule now on that. Okay, so this is where we get to put it all back together again. I get a bunch of derivatives here with respect to Q of the dynamic gamma metric. So what we're doing is we're just using the formula here for the metric coefficient derivative, the G derivative formula, back several pages here, for the covariant Christoffel coefficient array. Okay, and so I go ahead and I just write this as that plus this to match this, and I already have a half right here, so I take the half out and I get just what the doctor ordered here. This thing matches this, you see. So when it comes time to calculate the Christoffel coefficients, we'll only be calculating the ones we need, because we'll just go through and take a time derivative like this and then arrange it to read off each one of the coefficients here. So that will be the covariant Riemann equations, which has a momentum that has a covariant matrix attacking a contravariant thing and turning it into the covariant to match the covariant force. So this is the GCC equations that we're really used to. It's just being written in this funny language with the Christoffels. Is that making some sense? Okay. There's the contravariant. I go through with this gamma to change the indices wherever I can. On this page, the only thing that changes is this L becomes a K up here to match the covariant force that also got moved to contravariant variety. Okay, so there's the contra Riemann, there's the co, and where are they on the wall in this room? They're sitting down there, waiting to bother you, right in the middle of the thing. If I could get, I have so many of these things, and the batteries are in various stages. This guy right here is the one that's completely covariant. So that's the one, if you open up a GR book, you'll probably see that one. You may see this one, but most likely you'll see what we call the contravariant equation, which is this one right here. Okay? So far, so good. All right, let's go ahead and use it. Cylindrical polar. All right. And remember, I asked you to just go ahead and work the spherical out and then let it go morph into cylindrical. That's a quick way to get cylindrical, right? I hope that. It looks like a lot of you did that, but this would be what you do if you didn't know about spherical coordinates. This is just polar with a z added, right? So our polar coordinates we had before, and then we got a z tacked on there, which doesn't do much. The matrices are all 2 by 2, so this is a pretty easy thing to work out just on the board here to see what these coefficients are. Remember that we then could make covariant forces by using the Jacobian to transform Cartesian fx and fy and even fz, but it's not interested in playing the game because it's orthogonal to the other two on constant. So this is the general relation that you'll force, and this is what it comes out to for this particular set of equations, cosine and sine of the polar angle. Okay. Then the kinetic metric. Okay. Just a single mass is involved here, multiplying all of the Jacobian products, and that's another way to state it right there. So this is what we're looking at as far as the metric goes for this polar coordinates. And it's a diagonal one. There aren't any off-diagonal components here. It's an orthogonal coordinate system. So contravariant is just 1 over each one of the expressions here. This one, like this one, is just the mass. This is the only one that gets a rho squared. So what we're looking at here is inertia, rotational inertia, moment of inertia. m rho squared, m radius squared. And then this is the inverse of that to do a contravariant description. Okay, so there's the Lagrangian right there. No potential here, we're just doing kinetics. Okay, and there's the covariant momentum. Go ahead and take the partial derivative with respect to the velocities of each of the coordinates. Okay, and there is the angular momentum with respect to the polar coordinate. Remember how we pointed out that that's something that happens automatically when you follow the Lagrangian stuff. Now we're trying to make the Lagrangian into Christoffel stuff. So what we have to do is take the stuff that we've got here and go ahead and take the time derivatives that it asks for us. So I'm holding this up to you as a much more efficient way to get these things. Okay, instead of using this formula and going through all 8 of the possibilities, we just go ahead and force the thing to give us, by this 4-wheel drive equation here, the Christoffel form. In this case, it's the contravariant, the covariant form, and we'll be doing the contravariant shortly here. So for rho and phi, we need to do this. We don't need to do anything with z. It just sits there with nothing much else to add to us. So I go ahead and do the time derivative of this, the equation that of the kinetic thing we're doing here. Do the time derivative of the thing. That's the time derivative of momentum. Okay, so I got to do the time derivative of that thing right there, and then I've got to do subtract a partial derivative with respect to rho of the kinetic thing, and the only thing that has a rho in it that we have here, this guy, this doesn't have a rho, it just has a rho dot. This guy gives me that, okay, and we're done with that part right there. See if the other one here is for phi, okay. Now, in this case, you see what we're doing is we're matching what is the coefficient, what is this coefficient of the coordinate dot expression. That's a quadratic coordinate dot expression. In this case, it's just a coordinate dot squared. Okay, so this thing right here is the Christoffel coefficient, phi to rho. And then over here, the same game we're playing. Okay, it's now with respect to phi. Okay, instead of rho. So what we're getting here is a rho phi coefficient. Okay, we've got the m corresponding to rho, and then we've got the n corresponding to phi, but could have been the other way around. This thing is supposed to be symmetric in m and n, so you get an extra factor of 2 here when you add up everything that this gives. And that's something I want to make sure you notice, that it's going to be 2 times the product of the radial velocity with the angular velocity. So this is Coriolis coefficient we're looking at here. Okay, so here's the expression. Both rho phi phi and phi rho phi, just flipping that index doesn't do anything. Both of those are m rho. So I get 2m rho in the actual differentiation here. I have to remember to take that 2 off if I'm doing an off diagonal. So this very quick method is quick, but you can make a mistake by a factor of 2 very easily if q is not equal to p in the Christoffel derivation. Gamma qp or pq, they're both equal. Always will be equal. I should warn you, there's something called non-Riemannian space analysis. It's where you try to have parallel universes and things don't meet. It's very crazy, and they have Christoffel coefficients that aren't symmetric. And they still get that stuff published. It's been going for 20 years. It hasn't yielded much. It's part of string theory. Okay, so these are the contravariant equations, which really are acceleration equations. These things all take that don't have any m's in them. Okay, when I go do this one, everything is written directly in terms of the variables and their velocities in accelerations. So here is a typical, this is with gamma phi being 1 over m rho squared. So I stick that in there. Here, let's see if I've got that right. If I stick it here and here, okay, that's the definition for the contravariant force, okay, and this would be a sum if it was dummy indices. They're not dummies. These are radii, and these are phi. So you just have a product, a simple product. In any case, that leads to these expressions here for. Now we're talking about acceleration. So we're talking about Coriolis acceleration here. We're talking about Coriolis force up here. You've got an extra m in there that a force would have in terms of acceleration. Okay. So if you get good at this stuff, this is a quicker way than just going through the Lagrangian and pulling the stuff off that gave us this before, when we were marveling at how the formalism of Lagrange is so powerful to let us have all of these physical expressions for Coriolis things, which are very hard to visualize, and an equation of motion. This is the contravariant Riemann equation right here. So we're talking about centrifugal acceleration plus whatever nature provides outside. And here is Coriolis acceleration plus whatever nature provides that. We didn't have that distinction. I mean, we could have made it just by dividing by m, basically. But the idea that these two kinds of Riemann equations really are different physically, one referring to one of these that don't have the mass and others that do. And remember that the contravariant momentum is velocity. Right here, the m's gone. Okay, we didn't point that out before either. Okay, so there is some elegance creeping out of this otherwise almost indecipherable on the first day mathematics. Okay, and you know, I'm trying to sell it, right? You can tell that, right? Yeah, don't ask me who pays me to do this. Okay, now when we did this, we pointed out that hurricanes, and this is from last year's lecture, or that's 2 years ago actually, October 23, 2015. One of the things you notice is that the hurricane we had, Maria, I think it was the one we had, the one that made such a mess of Puerto Rico, it had a much more defined eye, and it was bigger, much bigger than this. So the global effect of having bath water in the ocean is very obvious in this business. There's more pictures of it. Some kind of crumbly in there, but take something that's this big and an eye about the same size but really sharp. You've got Maria and all her deadly stuff that she's playing for. Now, what I'd like to do is real quickly go through the problems a little bit here that came with making a vortex, and then we'll show a movie from Physics Girl that does a vortex in a swimming pool, and a very revealing one. So what we were talking about here is that shape right there, which occurs here, okay? Now, if I didn't have this thing going down the drain and just somehow got it to stop adiabatically so that it was still spinning, what you'll see, and most of you did this problem correctly, so I'm not going to do much more than point out that the parabola that hangs onto this 1 over r squared thing does so with the same geometry as the sophomore physics Earth, provided you let this describe the force and this the potential, right? So it's a little cockeyed analogy, but nevertheless there's a 1 over r squared for the force outside of the Earth, right? And then it becomes a linear force inside whose potential is that. Okay, well this thing just does it straight away, puts the parabola x to the positive 2 power right next to x to the, or r to the minus 2 power, okay? And this one is the result of having rigid rotation where the viscosity of the water takes over and makes a dimple, which you'll see in the movie physics girl doesn't mention these details, okay? But you'll see the effect of those details in one of the things she does. Okay, so let's run the movie. What I'm going to try to do, I guess, is to put it on the center screen. Good luck, huh? Let's go ahead and see if I can pull this up. Now, what I have to do here is see if I can, I don't see my cursor anywhere. Where did that cursor go?
Use your touchpad temporarily.
Let's see if I
It's
can
live.
just do it with my finger. That should be enough. There it is. Let's see if we can get this movie going here. There they are, with a parabola at the bottom. But what's really neat is when she sticks the die in. And you realize
I made a
those
video
two are
recently
connected.
on one of the simplest but most mesmerizing phenomena I've ever discovered. You drag a plate through the water, creating 2 dips on the surface, and sunlight shining through the dips will create 2 crisp black spots on the bottom of
That's
the pool
neat.
that can
The
persist
optics.
across the length of the pool. But the dips in the water are just the tip of the iceberg, as they say. Underneath the surface is an entire half-ring vortex, aka a toroidal vortex. I had never seen these before, so there's so much more to explore. And I know not everyone else has a pool, so I took some of your awesome
Isn't that
suggestions and I'm going to try them out.
For this one, I have to get in the pool. I know I look ridiculous, but this is not warm.
You can see here as the food coloring is dropped into the dips. The best part, I think, are the reflections you get off of the surface.
Makes a ring.
I couldn't see what I was filming, but this just looked way better than I could have imagined, so we tried 2 in sequence.
The red one cut the green one in half. The red one didn't die, but the green one kind of disintegrated. It was cool.
Yeah, it's interesting when they
And of
collide.
course it runs into my camera and dies.
The vortex hit on this end of the camera, and then you could see the depth of the vortex just moving along the rest of the vortex. It almost looked like it was unraveling, which I'm hoping won't happen here. We're gonna put the pole in the pool and let the vortex pass by so that the pole cuts it right in the middle. And I'm hoping that it'll meet back on the other side, or it'll split into 2 vortices.
Now this is really interesting because one vortex
Oh, it
goes
just kills
inside
it.
the other.
I think there's too much turbulence when there's an asymmetric collision of the vortex with an object in the water. Unlike when you hit a wall with the vortex, it's a lot more symmetric and it can keep that nice laminar flow and the spin of the vortex. I've been told that yellow is not the best color for a pool, so we're going to try blue and red to see how the fluid mixes. Nice. That looks awesome. It almost looks like the red is engulfing the blue. It's surprising that the colors
Yeah,
don't
see
mix
that?
together. It's almost like they stay in their own layers of the vortex. We tried a smaller plate just for fun. Check that out.
There, you'll see it there. No, not quite. Now this is interesting.
I was a bit surprised by this one. I thought the ping pong ball would disturb the flow of the vortex, but it dropped right in and shows us how fast it's spinning,
It's sitting
at
on a
least
rigid
close to the
rotation.
center.
I thought that was cool.
The motion of these vortices is really unpredictable. Like, sometimes they just seem to die for no reason. Sometimes they turn, Sometimes they hit the wall, sometimes they spread out, sometimes they go faster. When it's spinning too fast, there's a lot more turbulence, and that breaks up the vortex. And if there are disturbances on the surface, that actually causes sort of that unraveling death of the vortex to move across it.
But I guess the unpredictability is what makes fluid dynamics so fun
That's
and
cool right there.
beautiful.
Thanks for all of the great ideas, and thanks for watching.
If you've enjoyed these videos and would like to see them continue, head over to www.physicsgirl.org/support.
There you go. And there's lots of other stuff, some of which we'll be talking about later on in this. Okay. I should show you one more thing about the vortices. If we could do this, we'd end tornadoes. Of course, we can't do it, but if I get the thing spinning this way and I have that vortex, it's very stable, unless I do this, completely destroys it. What's happening is the Coriolis force is, as we'll see when we study it in more detail, a result of the turning of the environment. Whatever the thing will try to line up with the current rotation. So if I've already made this thing go with a rotation that is clockwise, say, that's just getting it going there, it's very happy to line up with me. But then I say, hey, I want to go the other way. It, as a rotating thing, has to turn its vector all the way around, and that screws it. So if you could somehow turn just a little bit the other way, the tornado would disintegrate. And you saw the vortex hitting things and disintegrating when they weren't the right symmetry in that little pipe. So those are things just to think about. Okay, let's get back here. We've got a couple more things to take a look at here. Effective potentials we've already discussed, so I can roar through this, I hope. But I'm giving you a problem on effective potentials this week. That's the cone. This is the eyeball that we're looking at here today. Basically it's a sphere, spherical coordinates. Let's see, this right here is cylindrical, so that is one that I go through very quickly because we've already gone through this. This is where you get an effective potential. Okay, remember the angular momentum squared over 2m radius squared. Okay, and then plus whatever else nature provides as a function of rho that you might also have. But we already get enough interesting physics just from the one of those. But if you put some gravity on it, that's a hard thing. Now, I should point out that what we're interested in when we do this, usually, is an expression that gives us the rho dot and the phi dot just in terms of something that's constant. In this case, the constant is the momentum, p phi. So p rho, not necessarily constant, but p phi definitely constant, making what we call the effective potential. That's this thing right here. And then it's just a thing about the momentum and velocity in the radial direction, the only remaining independent variable. Now, you have two choices for singularities. One is a nice quiet harmonic oscillator, another one is an unstable place. We've seen both of those in some of the things, and we'll see some more later on. But getting the spring constant of the remaining oscillator to figure out how fast the radius oscillates, and then comparing that to the how fast the actual rotation is, phi dot, okay? And the orbit will be closed, periodic orbit, if you can have an integer here in rho and another integer, or the same integer, which would be very often the case, 1 to 1, for the angular. So most of the time that we've been working with here, we've had this case as the one we haven't really studied yet, but that's in a Coulomb field, this is an actual ellipse with its focal point at the center. With our harmonic oscillator, this is also an ellipse. It doesn't have that little dip. This is an artistic drawing of possible things with a 2-to-1 ratio between the radial. The radial is going twice as fast as the thing is going around. Here the radial is going exactly with the frequency of the orbit itself. And then there's the other way around, 2-to-1. This one is very strange, and I haven't been able to find an easy system that obeys that one. 2-to-2 is the same as 1-to-1 is 3-to-3, 4. The diagonal is all the same here, but look at all the possibilities that you have with these. And each one of these, you have situations on just one side of the thing. If you have, for example, the radius and the angular frequencies exactly the same, or just a little bit above, if they're exactly the same, then it's the like the Coulomb orbit. But if they're just a little bit above that, then it precesses. Okay? And it retrograde precesses. If this thing was orbiting that way, the precession is opposite to the orbit. The red being opposite to the precession vector there, which is bringing the ellipse around. Then if it's just below 2, then you get retrograde precession. This is retrograde right here. This is prograde, or just below 2, you get them, so the precession is in the same direction with these. Now we get both of these for the problem that I'm going to take up next here, which is one I would have given, I think, last year. This is just a something rotating, sliding around in a ball.
It's over here.
And the eyeball is, thank you, right up in front here. So Daryl Henschel from the local Free Thinkers gave me this, and I immediately made a problem out of it. But if you just have the thing close to the bottom, and all the balls kind of go together on this, but the friction causes it to damp out fairly quickly, you make a 1-to-1 situation. But if you're really spin it up, you see it precesses because it's midway between 2-to-1 and a 1-to-1. The 2-to-1 is what you get when you're really near to the equator. And then as you drop from the equator, you start to see the precession. It's a little difficult to see the precession of this unless you get one ball to do a dance separate from the others. And that's a little hard to do. I won't try to show that one. But I'm going to zoom through this problem, which you should review on your own with some time. There's a metric and all that stuff. There's the kinetic energy for spherical coordinates. But now we're keeping the radius constant. We're all going to be on the sphere with this, going at different azimuthal angles and different polar angles is really what we're doing. So this is an effective potential here with respect to let's see, the delta is the momentum squared, angular momentum squared over mr squared. That's this thing. There's the angle exposed, and gamma is just the gravity, and then the alpha is just the mr squared over 2 of the kinetic angular inertia part. So we find an equilibrium point, a stable orbit on this thing, and then figure out what's the frequency of that. Okay, that is the inertia, inverse inertia, and the double derivative of the effective potential with respect to the angle we have oscillating. So what you can do is take that thing and then compare it with the phi dot. That is the azimuthal frequency. So working all the derivatives out and things like that. It makes a pretty simple expression, involving 1 plus 3 cosine squared. You'll get a similar expression, but not the same expression, for the oscillation of a ball in a cone. Okay, and that's something you can try very easily at home. Lots of funnels available that are big enough to do that. In any case, we start out at the bottom with a nice little sort of semi-elliptic orbit. Very quickly get something that's between 2, less than 2, but greater than 1. And then finally, if you get things right on the equator, you can actually see this thing stop recessing. So that's the eyeball. It's kind of an interesting thing, as I say here, ratio between 2 and 1. And most of the time irrational, but if this were a completely friction-free thing, you could drive it through various combinations of the 2 integers that make the figures that you saw in that diagram. Okay, and finally, we're going to have several problems on cycloids. We're going to do electromagnetism Lagrangian next time, and the first thing we'll see there is the cyclotron motion, which is cycloidal very often, and all kinds of cycloids pop up here. And then we'll come back to rotating sticks, pool ball bumpers, and stuff like that. So this particular expression for the simple pendulum, remember, became this thing for the cycloid. So I want you to go through the mathematics of proof what you already know about this particular gadget here, and also what's the geometry of this. To help you with that, I've handed you some graph paper in which I want you to produce by hand this time. No Mathematica, no MathCAD. This one I want to be proactive. Okay? And so you really understand what's the geometry, and it's quite beautiful. Worth having to pin up on your wall if you do a beautiful job of it. So this, of course, is a non-Platonic, non-Euclidean construction, because I have to be able to know pi. Pi is not constructible. So we're disobeying Euclidean rules, but we have graph paper, and we're just setting this thing up for you here with the irrationality built in. And from there, it is rational and quite beautiful. So we'll let you tussle with these for this week. It's partly German, partially French, and partly Irish. So all of the European cultures are in here. Okay, and with Millie, we're getting some other cultures. So, and you're bringing the Asian into play here. So we're having fun. Okay, we'll begin the electromagnetic mechanics on Thursday.